Let's get started. Today what we are talking about is sound. We're still continuing with sound. We're going to talk about one more characteristic of sound. On Monday will be the last characteristic we're going to discuss. Womp womp, womp womp, womp womp. You're in. There's a lesson. You're in your car. You take the radio knob, or the volume knob. You turn it up. What changes? Be more specific. It gets louder. Okay, then we would say it gets louder. Okay, so if you turn up the volume, it gets louder. Does it sound different?
Yep.
Other than being louder.
No.
I mean, sometimes maybe you can turn it up enough to where it'll distort the sound or something like that. I'm talking about if you just turn it up one or two places, it gets a little louder, but really doesn't sound any different. Does the beat change? Does the pitch change? No. Do the words change? No. Okay. So what we're going to be talking about today, what changes with the sound wave when you change that volume? Okay, we know it sounds louder, but what is the physics behind that? What is actually changing?
How old is this vibration?
Huh?
How old is this
I don't know. It's got a CD there. Okay, guys, the difference between a loud sound and a quiet sound is going to be the amount of energy carried by the sound wave. What do y'all think the relationship is going to be between the energy and the loudness? What's the relationship? What's going to be the relationship between the energy and the loudness? You increase the energy, you increase the loudness, right? More energy in the sound wave, the louder the sound wave is going to be. Okay, so if a loud sound has a lot of energy, then therefore you could come up with the idea that a quiet sound doesn't have a lot of energy. Okay? Sorry. So loud sound, a lot of energy. Quiet sound, not a lot of energy. No. So, let's go. Y'all seem like you're getting a little sleepy over there.
It's Friday. I told you that.
The amount of energy in the wave, guys, is going to correspond to the wave's amplitude.
You teach like that.
Teach like what?
Like that.
Screaming.
Screaming. Okay, so my voice right now, the sound, a lot of amplitude. In terms of a transverse wave, a lot of amplitude means what? What does a transverse wave with a lot of amplitude look like? It goes really high and low, right? Okay, it's tall. Okay, but sound is a transverse wave. Starts with an N. No, sound is a compressional wave. Okay, so for a compressional wave, the amplitude, if you remember, is related to how dense the compressions are and how not dense the rarefactions are. All right, that's going to come back. Don't fret. It's going to come back. So in terms of a spring, I'm going to draw it under here. It's going to go up there in a second. Okay, in terms of a spring, can y'all see compressions and rarefactions there? Yeah, I see a compression here, a compression there, and in between are rarefactions, right? Okay, but is that really clear? Start with an N. No, okay. So if I wanted to make that clearer, then I would need to take those rarefactions and I'd need to spread them out, right? and I need to make the compressions, and I would need to make them closer, right? Okay, so you see how the second wave, if that's a spring, the second wave is a lot easier to, the density or the compressions are a lot easier to see in the second wave than they are in the first wave, right? That's the amplitude. The easier it is to see the compressions and the rarefactions, the higher the amplitude is. Eh? Oh, no? What? Yeah, that is quite a ratchet spring. Okay. So to put that in, did y'all get that?
No, we didn't get that.
Okay. All right, put that into words, guys. Those areas where it was easy to see, those springs are really close together. So it was high density. And the areas where they're really spread out, that's low density. Okay, so if I have really high density, really low density, that's high amplitude. Okay, so for a really loud sound wave, the particles and the compressions would be really close or really tight. And for a really quiet sound wave, the compression a little looser. Okay? To put that into a picture with sound waves, okay, we'd see something more like that. Okay, which one of those has higher amplitude, the top or the bottom? The bottom. Okay, you see how the bottom is just, it's more obvious looking at the bottom that there's a compression wave than it is the top. Okay, so that bottom one is a higher amplitude. Which one's louder? Top or the bottom?
Starts with a K.
Starts with a B. Okay. Sometimes as a teacher, we put a question out there and we let y'all flop around like a fish out of water for a little while. Gotta see if you actually know the answer. When it's multiple choice, multiple guess. Which one of those sound waves do you think travels faster?
Compression.
Bottom.
Guys, which one travels faster? They're at the same speed. Why? Because it's the same medium. Okay. All waves always travel at the same speed in the same medium, so they travel at the same speed, even though one's louder. Could those be? Oh, are those both making the same sound?
Yes. No, because the top one is doing less vibration, right?
Don't let his face fool you.
Yeah. That is so. I'm done.
Those are both making the exact same sound. Okay, only the bottom one is louder. Okay, so the top one might be and the bottom one might be Okay, same sound, louder. All right. Well, I told y'all that I used to be a professional wedding singer, right?
No.
No, I wasn't a professional wedding singer. All right, so when an object, guys, vibrates with low energy, it creates low amplitude, and when an object vibrates with high energy, it creates high amplitude. What do you think it looks like if an object vibrates with high energy? What does it look like?
It still looks like, I don't know,
Okay, if it's vibrating with high energy, then it's moving really far back and forth. If it's vibrating with low energy, it's not moving as far back and forth. Okay, so with the speaker, if it's turned down really low, you'd see it moving just a little bit. As you turn it up, you'd see it moving more. Okay?
You would think that if you turn it up, it would move quicker.
Okay, the speed of the speaker moving is quicker, but the frequency is the same. So in other words, it moves back and forth. The same. So it's kind of like picture if I put like 2 pieces of tape right here in the middle of the room, and I just walked back and forth between the 2 pieces of tape, and then you ran back and forth between the 2 walls, and I hit this piece of tape the same time you hit that wall, and I hit this piece of tape the same time you hit that wall. Well, you're moving faster than I am, but we're moving at the same frequency because we're hitting the pieces of tape and the walls at the same time. Okay, this would represent a quiet sound. That would represent a loud sound.
So you keep saying the amplifier part.
But no.
The amplifier part is very loud.
No, I'm saying a speaker moves back and forth more when it's loud. Yes. All right. Okay, so if that's my speaker cone, remember we talked about the speaker cone. In a quiet sound, it might move that much. In a loud sound, it might move that much. Okay. What speaker do you think has more room to move? A speaker in a stereo or a speaker in your iPhone?
Stereo.
In the stereo, right? I mean, this one in the iPhone is just smaller. So which one gets louder? Stereo, because it can move more. Okay. Also, because it's bigger. That does help too. Intensity. There's a difference between loudness and intensity, and we'll talk about that difference in just a second. Yes. Oh. Have I been hitting the wrong thing? Well, that hasn't been reported on the document camera.
You can go back.
Okay, so you know how you said yesterday with the speaker, like if you had 2 speakers and one of them was like turned to like 40 or the max or something, and the other one was like turned down real low. Is that how it was? What you said, like from running back and forth, and they're both
Yeah,
doing the same sound?
they're doing the same sound, but one's just moving more than the other one is. I have a friend. He bought a really big, expensive subwoofer to go with his sound system in his house, and he has hardwood floors. And when it hits a low note, it vibrates, and you can watch the subwoofer just kind of dance around the hardwood floor. It doesn't do it if it's quiet because it's not moving as much. But when it gets louder, it's moving more, it's vibrating more, and it just kind of dances around. What now? Okay, so intensity, guys, the amount of energy per time that's being delivered by the sound. We've talked about another thing that was energy per time. We called it, please? Energy per time. What do we call it? Starts with a P. Oh, y'all are killing me. Energy per time. Come on, guys. What do we call it? Starts with power. Yeah, that's right. Power. Okay, good. Okay, so energy per time, power. What starts with power? Power. It also ends with power. So intensity, the amount of energy that flows per time. So as you're increasing the energy, as you're increasing the intensity, you're also increasing the power, right? Okay, if it's energy per time, if you're increasing the intensity, you're increasing the power. So when you turn up the radio, you're increasing the intensity. It's going to require more power. Okay. Okay. Intensity is going to influence how far away you can hear a sound. If you and your friend, guys, are whispering to each other, okay, that's a very low intensity. Okay, so you can't get 2 miles away and whisper to each other and hear it. Okay, that's not enough intensity to travel that far. Okay, so therefore, since you're so spread out, you're going to have to be close together. Is it possible for a sound to travel several miles? Sure, but it has to have high enough intensity. Okay, so like a thunder or a lightning strike, okay, that would have much higher intensity than a whisper would. Okay. What now?
What is atomic bomb?
That would have extremely high intensity. There was the largest atomic bomb ever dropped was called the Tsar bomb, Tzar, or Tzar, and it was I want to say 500 megatons. It's either 500 megatons or 50 megatons. I don't remember. 500 megatons. And the vibrations from that were measured going around the world something like 8 times. Was it 10?
So you
But I-
think that one bomb should be
It was. That's what Gladys said. So 1964. Now I know it was in the height of the Cold War.
Look it up if you don't believe
It was after World War II.
Yeah, it's,
I did say
Yeah.
there. I didn't say
Shouldn't be
when.
no more.
Yeah,
Hey, this is-
I don't know what year, but
Actually, this was after Cold War when they tested the bomb.
You don't say what country.
I would be surprised. But it could be. You could be right. Russia. All right, loudness. Loudness is different from intensity in that loudness is not the same for everybody.
Because he can't really hear you.
Okay? Intensity, the same for everybody. Loudness, not the same for everybody. Okay, one sound to you might sound really quiet. It might sound loud to me. Okay, that's loudness. Okay, so it's the human perception of sound.
Woo, my stomach out. You can break on.
I don't want to talk about this next point. I'm going to skip it. Okay. Oh, the first point?
He said you can hear him. He said
All right, the intensity scale for loudness, guys, is called the decibel. Anytime you're at a concert and they're doing like audio testing, they'll go around with a meter, and that meter tells them how many decibels it is. Okay, that they're trying to see how loud the speakers are. They're trying to set it up for the proper loudness. The two numbers on the decibel scale I want y'all to know are 0 and 120.
Can't you only listen to so many decibels like every hour?
Yeah. Well, we can talk about that in a second. You'll remind me. 0 on the decibel scale indicates the minimum that the average human can hear. Okay, so the average human can hear something at 0 decibels. Below 0 decibels, the average human cannot hear it, but there can be a sound below 0 decibels. And maybe a dog could hear it, or maybe a microphone, a really sensitive microphone could hear it.
That annoying sound that a microphone makes when you put it by speakers.
That's feedback. Essentially, what happens is a sound comes out of the speaker. It goes into the microphone. The microphone picks up that sound, and now it's louder because it came through the speaker. So then it goes back to the speaker, it gets louder. Then it goes back to the microphone, it goes back to the speaker, it gets louder. So it just gets louder and louder and louder and builds on itself. Kind of like resonance. Where was that? Oh yeah. And 100, so 0, minimum a human can hear. 120 is our pain threshold. That's where you're starting to feel pain. Not the same for everybody. On average, okay, 120. Every 10 units on the decibel scale represents 10 times louder. Okay, so if I'm looking at, let me see if there's a power mower, okay, and the pain threshold is 10 times louder than the power mower. Okay. A blue whale. I was looking this up earlier. A blue whale is capable of making a sound at 188 decibels. Okay? So that is well above a jet plane taking off. I mean, there are not many things that you can find that are there. I mean, I looked up the 10 loudest things. I think it was number 3. Okay. Number 1 was some asteroid hitting in 1908. And they said it was several hundred decibels. At 180, okay, 180, that's where the hearing cells are dead. Okay, so at 180, there's no coming back. Okay, permanent damage can occur. I want to say I heard 95. Okay, if a sound over an extended period of time at 95 decibels, you can start to have permanent damage. Okay, but pain threshold 120, and every 10 increase is 10 times louder. Okay. Any questions? All right, guys.